India's first satellite sat broken before it even left Earth, frozen mid-development, unable to transmit a single signal. The engineers found the fix not in their labs, not in their most sophisticated equipment. They found it in a farmer's field. APPLE was the name. The Ariane Passenger Payload Experiment. A 672-kilogram communications pioneer, India's first 3-axis stabilized satellite, equipped with 2 C-band transponders and a parabolic antenna the size of a dinner table. Built over 4 years of intensive development by the Indian Space Research Organization, APPLE represented a nation reaching upward for the first time, reaching into the orbital space above the Indian Ocean. Launched in June 1981 aboard Ariane 1 from French Guiana, it reached its assigned position above 102 degrees east in mid-July, ready to serve as a testbed for telecommunications infrastructure that would eventually span an entire continent and connect villages with cities that had never communicated before. But before it could leave Earth, a problem surfaced that threatened to unravel everything. During pre-launch testing in India, the telemetry and tracking systems couldn't establish a proper signal. Information bounced backward instead of traveling outward. Engineers stared at their instruments and watched the same failure repeat in measurement after measurement, an impedance mismatch in the antenna links. The electrical resistance between the cable and the antenna had to match precisely. If it didn't, signals would reflect inward, trapped and useless, unable to reach the Earth stations below. Without a fix, APPLE would launch as dead weight, a $1 million satellite that couldn't hear commands from the ground and couldn't send data home. Here was the crisis. ISRO had no facilities in India equipped to diagnose and solve this specific problem. The nearest advanced testing labs existed thousands of kilometers away. Building new equipment from scratch meant weeks of delay. It meant money the organization didn't have. It meant risking their entire launch window and potentially losing the mission. The launch was scheduled. The window was fixed. Every day of delay increased the probability of cancellation or postponement that could last months. Every engineer in the room understood the mathematics. They had a problem they couldn't solve in their current location. Then came a question that nobody had asked before. What if they didn't try to solve it in the lab at all? What if they took the satellite outside, to a place where the Earth itself could help them? Engineers placed APPLE on a Bullock cart. Not a platform of steel or aluminum, not a laboratory fixture made from refined materials, but an old wooden cart pulled by cattle. They drove it to an open field outside the city, far from power lines and metal structures and the electromagnetic chaos of urban development. No interference. No distortion, no metal walls to reflect and confuse the signal traveling to and from the antenna. Just earth and sky and a 672-kilogram satellite resting on wood and rope, exactly as nature intended. They set up their test equipment in that field and watched their instruments come alive. The impedance mismatch appeared immediately, clear and measurable in the clean electromagnetic environment. The metal walls of their lab, the power systems hidden in the walls, the grounding fixtures embedded in the floor, all of it had been masking the true problem, creating a fog that made the real signal invisible. Out here, away from all that, the signal revealed itself. Out here, the physics was honest. The antenna could show its true behavior without the interference of human infrastructure. 5 hours of testing. 5 hours to diagnose and adjust and understand and correct. By afternoon, they had resolved the impedance problem. The electrical balance had been restored. The antenna and cable now matched perfectly. Signals traveled outward instead of bouncing inward. The cost of the entire solution? 150 rupees to hire the cart. APPLE launched on June 19, 1981. It reached its operational position above 102 degrees east and began transmitting to Earth. Success came almost immediately. Almost. One of the 2 solar panels failed to deploy, a critical setback on a first mission. The satellite would operate at half power, limping through its designed lifespan instead of thriving through it. Every engineer who had worked on the mission felt the weight of that moment. They had solved one crisis only to discover another, yet APPLE endured. For 27 months it functioned, far longer than its diminished electrical budget should have permitted. Every month in orbit was a lesson about geostationary satellites. Every signal sent back to Earth carried data about antenna performance, transponder reliability, and how spacecraft behave when pushed beyond their limits. APPLE became the foundation for everything that followed: the UNISAT series that would blanket India with telecommunications, the GS8 constellation that would follow, and eventually a satellite fleet serving billions of people across the subcontinent and beyond. The Bullock cart wasn't just a clever workaround. It embodied something deeper. It showed that sometimes the answer to a space-age problem doesn't hide in your most sophisticated equipment. Sometimes it requires you to step backward, to remove the noise, literal electromagnetic noise, to find a place where the fundamentals of physics could speak clearly, unobstructed by the artificial world humans had built. R.M. Vasagam led APPLE through development and operation. He was the project director, the person responsible for every decision, every delay, every crisis. He understood something that many engineers miss: that resourcefulness isn't born from abundance, it's born from necessity. The engineers who have the least to work with often find the most elegant solutions. A farmer's field had taught them more than a laboratory ever could. An open sky had revealed what metal walls had hidden. Cattle had carried their satellite to the answer. And in doing so, they had taught a lesson that would echo through Indian engineering for decades. Sometimes you have to think like the simplest problem solver to solve the most complex problems. Today, India operates one of the world's largest satellite fleets. It maintains communications that connect villages and cities across the subcontinent. It provides weather data and disaster management. Its satellites reach 1 billion people every day. And somewhere in that legacy, deep in the DNA of Indian space engineering, sits the memory of the moment when a team of scientists made a choice: to think like farmers, to trust in simplicity, to move their million-dollar satellite onto a cart and drive it to a field. Because at the frontier, that's where genius lives. In the choice to abandon the complicated when the simple works. In the courage to look like you don't know what you're doing because you're willing to try something nobody has tried before. In the understanding that sometimes reaching for the stars requires you to stand on solid ground,